Hi class, welcome to the next section in chapter 11. This is 11.2. We're going to talk about direction fields and Euler's method. Okay. So, what is a direction field? A direction field is basically a graph where you plot a whole bunch of tangent lines. Okay. So what it does is it allows us to analyze the entire system of a differential equation, meaning we can look at kind of all the solutions at once by looking at a direction field. Okay. So remember that we have infinite solutions, a whole family of solutions, and when we have initial conditions or even sometimes boundary conditions, that allows us to narrow down to a distinct solution out of this family of solutions we have present. So a direction field kind of allows us to visualize that a little bit. Okay. So the way that we do this is we take our differential equation and we plug in a bunch of different points for x and y. And what we get out is the tangent, right? So remember what tangent is, the derivative, it's the rate of change at that instant. So we plug in a bunch of x and y values, and what we get is how our solutions or my function, how my solutions change at that point. Okay, so we're gonna just take x, y values um, out of our R2, right? Our x and y axis. We're just gonna plug them into the differential equation, right? And what we get out is a bunch of slopes of the tangent that passes to our solution at that point x, y. So this gives us kind of like a flow map. When I look at a direction field, to me, it looks like current in a river. It allows me to kind of see how the water is ebbing and flowing. That's really what a direction field does. Okay, so let's consider the differential equation. Y prime equals x times 2 minus y. Okay, so what we're going to do is we're going to pick a few points for x and y, actually a whole lot of points, and we're going to plug those points into my derivative. And what it's going to do is it tells me what the rate of change is, right? What the slope of the tangent line is at each of those points that I plug into my DE. So for instance, if I plug in 0 and 1, I plug in 0 for x, 1 for y, 0 times anything is 0, so I'll get out 0. Okay. So what I would do is at this point 0, 1, I would draw a small line that is horizontal, that has a slope of 0, right? Slope of 0 means I'm horizontal. So at the point 0, 1, I would just draw a small horizontal line, and I would put an arrowhead at the end of it, right? Because these are going to be vectors, right? All of these. So when I plug in 0, 1 into my derivative to my solution, I'm going to get out 0. Okay, tangent line is 0. So this is called an equilibrium point. If I plug in 0 and along this entire line, I get out 0, I call it an equilibrium, okay? Or also a critical point or a stability point. If I choose a different value to plug in, 1 and 1, I plug in x and my y, and I'm going to get out 1. So when I'm at 1, 1 on my graph, I would draw a short little arrow that has a slope of 1 at that point, and it's telling me that if I were to look at a solution curve through that point, the tangent line at that point would have a slope of 1. Okay, I'll plug in 1, 2, same thing, 1 and 2. This gives me 0, so I'm getting out the line or a horizontal tangent at that point. And I would do this so on and so on and so on and so on until I get basically an entire graph's worth, something like this. Now, obviously, I didn't draw this by hand. This is obviously on a computer. Generally, when we draw direction fields, you would want to use a computer to do this. We definitely, some old school instructors and some old school textbooks will have you actually draw direction fields by hand. I mean, just look at how many points I have. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Was that 9? So there's 9 rows and 9 columns. So there's 81 points. There's 81 arrows here, right? I don't have the time to plug in 81 points into my function and find 81 values and draw 81 vectors. That's a lot of wasted time. Okay, so we use a calculator, not a calculator, but some sort of technology. In order to do this, you can literally just look up direction field plotter, and there's a minute of them pop up. Okay, so in my class, whenever I'm giving you a problem that has to do with the direction field, I will obviously give you the direction field. Okay. Um, a direction field is similar to modeling the current of a river. You can see how this kind of comes down and it comes back up. It looks like there's some parabolic looking type solutions here. Here you can see the arrow comes down a little bit, and then all the ones on the y-axis you can see are horizontal. Okay, and then you can see here that this is horizontal as well, right? If I were to be here, the current, if this was water, it would just flow straight here. If this is water, if I'm looking at kind of what happens, like if I drop the ping pong ball into the river right here, I could see where the current would take it. Okay, that's how I think of a direction field, right? So when we start picking a point, we can follow that point through its tangent arrows because it keeps telling us which direction to go, and we can trace the curve of the solution that it would belong to. So let's kind of do an example of that. So let's say that I'm choosing the point negative 1, 1. So this could be the boundary condition on my differential equation. Well, if I look at negative 1, 1, and I drop a ball here, the solution that satisfies this kind of looks like this, right? It looks like it's sort of parabolic in nature. Okay, so then my solution curve would be negative 1, 1. Apologies, I said negative 1 and I went down 1. I meant to go up 1. Regardless, it's the same thing. So here, this is the same solution curve, direction field, but I did a lot more arrows. So here, this is 9 and 9. And so here I did much more than 9. So you can get a much better idea of the flow. And this is the actual solution to the curve at this point, right? So if I'm looking at what happens here, as you can see, the tangent line is telling me I'm kind of going in this direction. And so it ebbs and flows. Here, tangent is 0. And it's telling me to kick it back up and start going in this direction, right? So this is the solution curve. If my boundary condition is negative 1, 1, it would mean, boom, this is the function that follows it. Okay. If I said I'm going to go negative 1, negative 1, well, then my solution curve would be the one that goes down here through that point. And so for any point that I choose as a boundary condition or an initial condition, right? Let's say I start at 1 is right here. Let's say I was to start at 0, 1. Well, it's telling me that my function goes straight and then it's starting to go up, right? And it would be very similar to what I have here, right? Going in the opposite direction, it would kind of model the same thing. So as you can see, the more arrows that I have, the easier it is to see what the flow is for these family of solutions. Okay. Again, here it's saying notice that y equals 2. That's right on top, right? If this is 1, double that. That's this line right here, where all of the tangent lines are straight, right? All the derivatives are 0. That's why all the arrows are horizontal. It's called an equilibrium solution, right? This is an equilibrium. All of my functions are going to kind of eventually come up to 2 as time goes on, right? So if I were to pick this point, it's going to go up towards 2 and it would settle at 2. Even though we don't know what happens over here, it's always equal to 2. It's always horizontal here. So it's an equilibrium point where things are going to kind of flow back up towards it, okay? And so it's actually called um, not just an equilibrium point, but it's an attractor because it always brings stuff towards it from the bottom. Okay, so now we're going to go over a numerical method of solving differential equations. So this is the first example of us actually trying to approximate an answer. So as you can see, there can be an infinite number of solutions, right? And so using a direction field, we can come up with a method, this numerical method, which we call Euler's method, for finding approximate solutions. So first we'll talk about approximate solutions, and then we'll talk about how to find exact solutions. The reason we talk about approximate solutions first is because a lot of the times your differential equation is impossible to solve. Okay, now obviously in a differential equations course, we talk about specific types of differential equations that we can solve using different methods. That's what the course is all about. But in practice, in application, a lot of times the DEs that you come up with, you will not be able to solve directly. And so you would need to approximate an answer using a numerical method, right? So similar to how we approximate the area under the curve with Simpson's rule or trapezoid rule or something like that when it's too difficult or impossible to evaluate an integral, right? So using a numerical method to find an approximation when it's too difficult to find an exact value. So numerical methods for DEs, again, allow us to get an approximation of the values to a solution curve. Okay, that might be impossible or too difficult to solve directly. So there's several numerical methods, but we're only going to focus on one, which is again Euler's method. There are some very, very complicated, much more advanced, very, 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 very accurate methods. This is sort of the easiest, simplest, least least accurate method, right? So that's the one we'll start with. So Euler's method. So let's just jump into an example. Let's consider the initial value problem. Y prime equals y plus xy with the initial condition. When I plug in 0 to my solution, I get out 1. So for Euler's method, I really don't want, well, no, not want. I cannot have anything larger than a first order. Um, Now, if it's linear or nonlinear, it doesn't really matter. Nothing else really matters. I just need it to be first order. And I need to have an initial condition, right? Or some sort of boundary condition, but really I need an initial condition in order to do Euler's method. Like we were doing before with the direction field, I'm going to start off by plugging in my initial condition into my differential equation. So I know that the point 0, 1 is on my curve. So if I know that, and I have an equation for the derivative, I will plug these values 0 and y in so that I know what the rate of change is at my starting point. And then I can kind of follow that as a guideline to try to figure out the next point, find its rate of change, which should point me in the direction of the next one, and so forth, right? So we're kind of doing this step by step by evaluating a point, going down a little bit in that direction, choosing a new point, and doing it over again, okay? So uh, y of 0 equals 1 is the same thing as saying I'm looking at the point 0, 1. So x is 0 tells me that y is 1. So if I plug this into the derivative, okay, I'm looking at 0 in the derivative of my original function. That means I'm going to plug in 1 for y, 0 for x. This part goes away, so my slope at 0, 1 is 1. Okay. So the solution curve to this IPP has a slope of 1 at the point 0. So the line that's formed by this point has a slope of 1. So y equals x plus 1 in this case, right? And I know that because the tangent line goes to the point 0, 1, and it has a slope of 1. So y equals mx plus b, slope of 1. 0, 1 is a y-intercept, so it's very clear here that the line, the tangent line at this point is x plus 1. Okay, so then L1, the line that's tangent to my solution at 0, 1, um, is a linear approximation, right? So if you remember linear approximations from calculus 1, it means that that tangent line, as long as I'm close in value to the point where it touches, it gives a pretty good approximation for the values of my curve. Okay, so close in value to my solution curve, my my tangent line is a linear approximation. It gives very, very good values, but the further out I go, the more it diverges away from my solution curve. Okay, so and that's this next part. It's going to diverge from the actual solution curve for every x that is not sufficiently close to x equals 0. Since the solution to my DE is a curve and not a linear equation, so my solution is a curve, I have a line that touches it, so that curve um, will most likely bend away from the line. So the line and the curve are going to separate further and further and further as I move further and further away from their point of intersection. So my tangent line is only a good approximation close to the point 0, 1, close to the point where it touches the solution curve, right? So for instance, this is my actual solution curve. Okay, I'm not going to tell you what the actual equation is. We talk about having how to solve an exact solution um, in the next section, I believe, actually, yes. And so this is my actual solution, and this is my approximation. This is where the two are equal in value, right, where they intersect. And as you can see, as I move further and further away along this tangent line, the further and further away I move in value from the actual solution. So if I plug in a value that's really, really close, and I look at the slope there, it should be pretty close to the slope of my actual solution. But if I were to look out here on my tangent line and say, oh, what's happening here? Well, it doesn't really matter because I'm so far away from the actual solution that it's not giving me a good approximation anymore. Okay, so what I really want to do is I'm going to look along my tangent line just a little bit away from where I have my point of intersection, where these things look like they're the same value, but there's actually just a very, very small difference between them. Okay, so this is what the direction field looks like for um, for my solution. And so if this is the point that I need to lie on my solution, well, then that's how I know. So you can see here, this is telling me to go forward and up. So it comes up, and these arrows are telling me that it moves this way. If I trace it backwards, I'm going against the grain, right? So I'm going in the direction of the tails. So this is my tangent line, right? Because the tangent at this point is telling me, that that's what the line is. So my actual solution, which I don't actually have, I'm just showing it to you. We have to adjust our approximation by looking at the tangent line because we don't actually have this blue function. Okay, so we're going to look at a value very, very, very close to this point of intersection. Okay, and then we're going to plug that into our solution. So we're gonna plug that into the equation that gives me all of the tangent arrows, tangent vectors, and we're going to use that as the next point. Okay. And now the distance that I move away from my initial point x naught, I call it h. And every time I move, I'm going to move at a distance of h. And I need h to be small. Okay. The smaller, the better. But obviously, if it's too small, then I got to do this a whole lot of times in order to get any sort of distance going, right? So I don't want it too small because then it just creates more work. But if it's too big, then it makes me have a worse and worse approximation. Okay. So this value h here that we move each time, I call the step size because every time I'm moving a step, right? So here, let's say that h is 0.1. It's not a large value, it's small. Um, Obviously, if I want to draw a long curve, if this is going by 1, that's 10 approximations just in there. If I'm going to 2, I need 10 approximations here in order to try to follow my curve out just 2 units, right? So, but we want it to be relatively small so I can get a good approximation, right? So if this is a value of 1 here, this is a half, 0.5, 0.1 would be somewhere like right here, right? So I'm not too far out. If I went out a whole distance of 1, this is with the approximation value I would have, and the actual value would be up here. And that's already a difference of more than 2, right? That's a really, really big difference in for what we're trying to do, okay? So my next point, which I call x1, is my previous point plus my step size h. So since I started at 0 and I'm moving by zero point 0.1 each time, well, my next value is 0 plus zero point 0.1 or just 0 0.1. So I'm going to take 0 0.1 and I'm going to plug that in to my equation, okay, into my line. So I plug in 0 0.1 into my line, I get an output, so then now I have a point, right? So if I plug in 0 0.1 into my line, I get out 1.1, and so the point 0 0.1, 1.1 is a point on the tangent line, okay? This is the new point is on my tangent line, so I want to see what happens here in regard to my differential equation, right? So I'm going to plug this into my differential equation so I can see what the actual slope is at this point, right? So I'm going to plug 0 0.1, 1.1. So the derivative at 0 0.1 is going to be 1.1. So this was y plus x times y. And so when I get the answer out for that, it's 1.21. Okay. So at this point, 0 0.1 and 1.1, my approximation is telling me that I have a slope of around 1.21. Okay. And so I make a new tangent line using this point and this slope at the point, right? I'm going to call that L2 because it's my second tangent line. And so I'm going to have y equals mx plus b. The only thing I don't have is the b. I know y, 1.1. I know m, which is the slope, so 1.21. And I know my x value, it's 0.1 more than where I was before. I just don't know the y-intercept, so I solve for b. So basically 1.1 minus this product, and that is 0.979. So my tangent line then at 0.1, 1.1, so a little bit away from the initial point, is 1.21 times x plus 0.979. So if we zoom in a little bit so that we can kind of see what's happening here, this was my initial condition, 0, 1. I had a tangent line at that point, and I followed that um, to 0.1 for x, away from x, and I found another point. So when I went over by 0.1, I plugged that value into my tangent line. I got out a new point from my tangent line, which is 0.1, 1.1, and I use that with the tangent that's here in order to, or the rate of change that's there, by plugging it into the equation for the direction field, to my differential equation, and I found a new tangent line, okay? And so that next tangent line then intersects at x1, okay? And I would do the exact same thing. I would move up along this line by zero point 0.1, and I would plug in to see what's happening at 0.1 away. So I was at 0.1 before, so now what I got to do is I got to plug in 0.2 into this line, the tangent line, okay, L2. And the output I get from that, I then have to plug into my differential equation to find the slope there, so that I can use that as to find the next tangent line, and so forth and so forth. Okay. So for our next approximation, we need the point x2, which is again just 0.1 more than the previous. So I was at 0.1, so I'm going to move 0.1 more, so I'm at 0.2 now for my x value. I plug 0.2 into my new tangent line, and I get out the rate of, I get the output on the tangent line. So then that gives me a point. So on the second tangent line, I have 0.2 and 1.221. Okay. And now I can use those two values with my derivative function to figure out what the rate of change is there, right? So 1.221 is our approximation of the solution at x equals 0.2 by using that tangent line. Okay. So for the next approximation curve, okay, that's what I got, right? So I'm no longer using all of x2, or L2, I mean. I just needed to use a little bit of it so that this distance from x0 to x1 is 0.1, and the distance from x1 to x2 horizontally is also 0.1, okay? And if I continue this over and over and over and over again, then I get something that looks like this, okay? So this is my real solution, y, and what I'm doing is I just keep finding an approximation. So I use the first tangent line with the initial value to find a new point. Then from there, I use that information to find the rate of change at that point, and then I find the tangent line for the next one. And I move along that tangent line for a little bit, okay? Then I plug in x2 to my function. I get the rate of change there from that differential equation, and then I use that point and that slope to find the next tangent line, and then I move along that tangent line a horizontal distance of 0.1, okay? And then when I plug that point into my third tangent line, I get a rate of change, right? Or I get an output. And so I use that point, I plug it into my differential equation, I get the rate of change there, right? Once I have the rate of change and a point, I can find the next tangent line. And I do it over and over. I'm doing the same thing repeatedly. And as you can see, I start off equal to my solution at that initial condition, right? That point of intersection. But as I continue to move out and out and out, I am starting to move further and further and further away from the actual solution. And again, that's because I'm using the tangent line. The tangent line is just an approximation. It's not the actual curve. So I know the tangent line is close in value, right? If I stay close, but the more I move out, the further away I go. So that's why if I use an even smaller value of h, I would be much, much, much more closer to the true value, but I would still diverge from it as I moved on over time. Okay, and so that is Euler's method. That is how Euler's method works. Hopefully that makes sense to you. If not, go ahead and pause it rewind it, listen to it one more time. It's okay, right? So we see that our approximation begins to diverge from the actual solution curve the more iterations that we have. The smaller the step size, the smaller the size of h, that's 0.1 in our case, then the better our approximation is actually going to be, right? Um, let's kind of look at these last steps in order to develop the model that we're going to need. Because right now, I just have it written to you as like as a concept. You're understanding it right now as a concept, as a process. And there's the step by step is not actually like um, formally written out for you yet, right? So let's go ahead and develop a method to make this a little bit easier to understand. Because it's going to be hard to remember exactly what to do each time. Okay, I plug in, I find the point, yada yada, right? So for the last point that I did here for x2, my input was 0.2, and the output on that tangent line was 1.221 for this tangent line approximation at that point that we have. Notice that 1.221 is written in terms of step size as the following, right? So I can write 1.221 is 1.21 times 0.2 plus 0.979. And I'm getting that from that tangent line approximation. So all I'm doing is taking 1.21. Here, my step size is, I'm just writing it as 0.2, right? The way that I got this 1.221 was me just plugging in x and y here, right? The output 1.221 happens when I plug in this x. So when I manipulate this a little bit, um, I can separate the 0.2 to 2 times 0.1, which makes sense because I'm taking 2 of my steps h in order to get here, right? I made 1 and then my second point in order to get there, okay? So recall that 0.979 was found in the same way, okay? This was the b value. In order to find the b value in a line, I plugged in my first step and the output that went with it on that tangent line L1 into L2. So this was my b equals um, y minus uh, m, the slope, times x, right? So that's how I solve for 0.977, not, sorry, 0.979 is I plugged it into y equals mx plus b, where this was my y, right? 1.1 is y, um, mx equals b, right? So if I was to solve for b here, right, just to be clear, I would subtract mx, right? I would have y minus mx equals b. I would have y minus my slope times my input, which was 0.1 at that time, would equal the b value, right? So if I go back to my initial problem, right, I told you that 1.221 was found by plugging it into L2. So this was the slope for L2 plus 2 step sizes plus b. So instead of writing 0.979, I am writing this expanded form of y minus mx for the previous line, okay? So now what you can see is that I have my step size here showing up, I have my step size here showing up, and I have 1.21 showing up twice, okay? So if I pull out that common factor, 1.1 is over here all by himself. I have 2 of these minus 1 of those, okay? So that turns into a 1. And so here I have my previous y value plus my step size plus my previous slope. And that is how I got my new y value. Okay, so looking at that another way, my second y value output was found by using my first y value and adding to it h times my derivative evaluated at that point. Okay, so y1 is the previous solution approximation, y2 is the current solution approximation, y prime of 1 is the slope of the previous linear approximation. So if I generalize this into current and previous, or next and current, um, my next output value is my current output value plus my step size times the rate of change at the point that I'm at right now. Okay, and so that is how I find each new output value. Okay, so again, I'm plugging x in and y in my current point into my differential equation. multiplying that times my step size, and I'm adding that to my current output, and that's what my new output will be. Okay. And so here I'm just modeling off of the process that we were doing. We're taking a point, finding a tangent line, move up a little bit, plug in a value to get an output at that tangent line, and then using that output to find the slope at that tangent line, and then using that point in the slope to find the next tangent line, right? So I could do it like that over and over again, but it's actually more work than just following this recursive formula here, okay? So let's go ahead and do this again, right? But instead, and if you look and see, I actually have a different equation here. This is plus xy. Let me just double check what we are doing before. Was it plus? I think it was. It was plus xy. So it's the same one, same equation. Just want to make sure. Same initial point, I believe. Okay, so what are we doing different? We're going to have a smaller step size. Okay. So this is my formula, right? This is the generalized formula that I'm looking at. Okay, the second one probably will make more sense to you. So let's use this formula from scratch for the previous problem we just did to find the Euler approximation to y of 0.5 for y prime is y plus xy, starting at 0, 1, and with a step size of 0.1. So we're doing the same thing that we're doing, but we're going to stop at 0.5. Even though we've gone 2 steps already, we're going to use this formula. We're going to start from scratch just using the formula instead of continuing to find the tangent line and what so have you. We're just gonna follow the formula, this recursive formula that we have instead. Okay. So my h value is 0.1, just like before. I'm starting at the same initial condition, and I have to do this 5 times because it wants me to stop at the approximation for 0.5. So here, I went up to x4. We would do one more. So I'm gonna have this to start off. I'm gonna do, so this would be 0.1, 0.2, 0.3, 0.4, and then 0.5 would be the next one. So I'm gonna find approximation for all of these, and we'll actually find the values instead of just the graph. Okay. We're gonna round our answers so that we stay with 9 decimal places of accuracy. Again, when you do calculations, you want to be as accurate as possible. And then when you give a report and answer, when you're, putting it into the application, that's when you round. But if you round stuff first and you keep doing math on rounded values, you have an error that accumulates. So you generally want to keep as many places as possible of accuracy until you're completely done, and then you can shorten it to however many that you want. But if you round as you go, you are going to accumulate error, and you can be off by a significant amount, actually, depending on the type of calculations you're doing. All right, so let's go ahead and make a table here. Here I have my current value of x, my current value of y. This is going to be the rate of change at that xy. And I just went ahead and wrote the formula here so that I can remember as I do this, or as we talk about it, you can see what the formula was, right? So y plus x times y. And so n is my current point that I'm at. And then here, we're going to use the equation, the Euler's method equation, in order to find the new value that I'm going to have for my next approximation output-wise, right? And so I have my formula. I'm going to use my current output, yn. I'm going to use my step size, which in this case is 0.1. And I'm going to find the value that I found here for y prime at my current x and y. Okay, so this kind of is all the setup I need in order to just find my next value, right? So we have our table. I start off at 0, 1, right? When I plug in 0, I get out 1. So I'm going to plug 0 and 1 into my DE in order to get the rate of change at that point. Okay, so I plug in 1 plus 0 times 1, and that is equal to 1. And then I'm going to plug everything into here. My output is 1 plus the step size of 0.1 times what I got for y prime at my current point, so times 1, right? So yn plus h plus the output at my current point, and that gives me 1.1, which, again, agrees with what we had way over here. Okay, cool. plugged 0.1 into my tangent line, and I got out 1.1. Okay, this was my approximation from the next point. But here we did it on the table, and it's much more crisp and clear because I don't have to do all this convoluted stuff. I'm just following the formulas that I have, right? Current x and y. This is the formula to give me the rate of change at this point. And then I use all three of those with the step size in Euler's formula. The Euler's method formula never changes. It's always this formula. This is the one that can change, right? The rate of change at the point that I'm at. So my next output now is 1.1. My step size is 0.1. So my next x is 0.1. My output is, I don't have to plug this into anything because I found this already. That's what this point is for. So now I plug this point 0.1 and 1.1 into my differential equation for the direction field for Euler's method, right? My current output plus my current x plus my current output, and that gives me my new output, which again, if you look over here, right, the slope for that tangent line was 1.21. Okay, it's a lot less work using this table. Now I use all three of these things and plug it in. So my new output is going to be my current output, 1.1, plus my step size, which is 0.1, plus the rate of change that I just found in this third column. Okay, and when I add those together, I get 1.221, which again was what I got here. Okay, that was my approximation. So we're just going to keep following that process. Okay, my next value of x is 0.2, because again, each time I'm moving by 0.2. My y approximation is what I found here in this last column. That just goes straight here. Now I use this point to plug into my dE to find the rate of change at this point, which is 1.4652. And now I use all three of these things, my point and the rate of change at this point to find my next point. So my current output plus my step size times the rate of change at my current point, and that is 1.36752. So again, I'm keeping 9 decimal points of accuracy. There's no values after this yet, right? So that's why there's only 4 decimals, only 2, only 3, yada, 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 right? So now as these answers become longer and longer, I'm not going to show the work anymore. I've already done it for, the first 3, so it should be easy to follow what's going on here. So my next x value is 0.1 more than it was before, right? That's my step size. My output I found here. I use these two values together in this column to find the rate of change. So that's 1.777776. And then I use these three things together along with the step size to find my new approximate output, right? So here I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7 decimals of accuracy. Okay. Now this is my new output here at 0.4. Okay. I used these two together in my dE to find the rate of change there. Okay. And then I use these three things together to find the approximation for 0.5, right? Because this is x naught, this is x1, x2, x3, x4. So I just need that output here, and that's my final answer. So this is what, 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places of accuracy. And that is my final value. That is my x5, right? My approximation at 0.5 is this value. Now that's not the true value, but that's my approximate value by Euler's method. Okay. So obviously, the question is, well, how good of an approximation is it? Okay, so we're not going to do an error analysis, but we will figure out how close it is. Okay, in order to find out how close it is, I obviously need to know what the exact solution is. Now, I'm not going to show you how to find the exact solution because that's the next section. 11.3, we talk about a couple of methods for finding the exact solution for certain types of DEs. I've gone ahead and already found that solution because I can actually solve this directly. And so the exact solution is y equals e to the 1/2 x squared plus x. Okay. And again, we'll talk about the methods for solving exactly the most basic methods are going to be in 11.3 and 11.4 as well, but 11.3 is like the starter section. Okay. So if I plug in 0.5 to the exact solution, okay, so everywhere I see x, I replace with 0.5. I get out 1.868245957. So it's relatively close in value. Obviously, it's not exact. Now, how close is pretty close? Well, I'm not that far away. I'm half a unit away from the starting point where I have an exact value. And so to only be a half a unit away and start to diverge this much, that's kind of a lot, right? In fact, we can see it because I actually did all of this work beforehand and I made it in a graph. So you can see how we're starting to trail. And so remember, the difference is this is the point I'm at and the point directly above it on the Y graph, right? So from here to here, I don't even have the point directly above it, but you can see that's much larger than it is here. So once I move up more, obviously that's a bigger difference. But here, this is also only 0.6 on the axis, right? I've only gone from 1 to 1.6. I haven't even gone up to 2 yet. So this is pretty zoomed in for this graph, right? Okay, so I have the exact value. I have my approximation. So let's actually find the difference there. Okay, so the error is my actual value minus my approximate value. So what are the difference between them? And that's about a tenth, right? So not a huge difference, but I mean, I don't know. Does this represent like a breaking point of something, right? How much a bridge is allowed to wobble before it snaps in half? That's kind of important. How much error do I want to have there, right? Before something might break and kill somebody. So um, it's really due to context, the amount of error that I'm willing to have, right? So my error allows to tell if we have an overestimate or an underestimate. So my error is positive. That means my approximation is under my actual value because the error is a positive value. So in order to have, that means my actual value is larger, right? So this is an underestimate. Okay. My absolute error is the absolute value of the difference, right? This is good for just saying how far off am I, period. Does it, if I don't care if I'm over or under, I just want to know how far away I am. That's where absolute error um, is important. So I'm just taking the absolute value. Since this is positive anyways, the absolute error is the exact same value, okay? Now, relative error is the percent difference, right? So I'm going to take my absolute error and I'm going to divide it by the actual value. Now, the relative error is a percentage. It needs to be positive. So no matter what, I'm really just doing this and taking the positive value. I don't really care about these parentheses and stuff and this absolute value marker. In general, I would just find this error and I would just take the absolute value of it. Okay. So here I'm looking, my absolute error is an absolute value anyways, right? The actual value is an absolute value. And so I'm just going to find the difference and I'm going to divide it by the actual value it's supposed to be. And that tells me what percent I'm off by. So my value is about 5.7% away. Okay. So I would just take this and turn it into a percent in order to talk about the percent relative error, right? So I have about 5% error in my approximation. All right. Hope this was helpful. I will see you guys on the next section.